they represent, but that's okay.
This conference will now be recorded.
There we go. And then for some reason, I can never get the little box off. There we go. The box is gone. Yay. Okay. So we'll just start with, we'll go through each. Like I said, I'm not going to, I'll at least get you started on each problem. The answers are there and attached. And, you know, obviously, if you have questions, stop me. It would probably, when I have the screen like this, I can't see if there's anything coming up in the text box. So every once in a while, I'll expand it and take a look, but you can unmute and pop on there. So, and I'll also talk about the tests as we go through this too. So the first problem is this line of best fit. So we have this small sample of data. And kind of regression analysis is all about how well does a small sample of data really represent the entire population, and can we eventually make reference inferences and predictions based on the regression equation that we came up with. So here we have a really small sample of data. The X values are 0, 1, 3, 3, 5, and there's the corresponding Y values. I don't even think this particular problem has a context, so we have no idea what they represent, but that's okay. And then we have 2 regression lines. And the idea is, here's 2 regression lines. Which one is the better fit for this data without graphing or anything like that? So when we do this one, I'm going to make it bigger so we can see it. Yay. So this is one where I'll go through just a couple of the points with you and then let you finish it, and you can look at the summations because the answer key does have the summations in here. We have a notation E. You can think of E as the error, or E as also called the residual. And what E represents is the difference between the actual Y value and the Y value you would get if you used the equation, okay? So let's start with our first X value of 0. And if you have a calculator, you can see, well, if X is 0 and I used line A, what would I get for Y? Well, it would be Y equals 7.5 minus 0.9 times 0. So that's just going to be 7.5. Okay. Notice the raw data has a Y value of 7. We got a Y value of 7.5. So my first E value, the residual for that particular point for line A, the E value is always equal to, these are called your Y sub i's, like Y sub 1, Y sub 2, Y sub 3, 4, 5, minus. Now, the regression line, we call them Y hats, minus Y hat. So this E value for that point, for that line, would be 7 minus 7.5, which is negative 0.5, correct? Please, and chime in with my math. Okay. Now, to determine the line of best fit, what we would do, so these are all our E sub a's. Our first one would be negative 0.5. We would take the summation of E squares from line A and get a total. We would take the summation of E squares from line B and get a total. And the one that had the smallest total, which means the smallest error, is the line of better fit. So if E was negative 0.5 squared, negative 0.5, when you square that, you get 0.25. Okay? So let's do the same thing with the x equaling 1. Still using line A. So now we have 7.5 minus 0.9 times 1. That's actually going to give me, that gave me 6.6. To find E, I take the original value of 6, subtract the 6.6. So 6 minus 6.6 equals negative 0.6. And then go ahead and square that. And that's 0.36. And you're going to do that for each number. So I'm going to kind of skip some of the work. So 7.5 minus 0.9 times 3 is 4.8. So 5 minus 4.8 squared is 0.04. When I plug in a 3, I'm still going to get 4.8, right? But now I'm subtracting it from a 4 instead of a 5. So 4 minus 4.8 is negative 0.8, and I'm going to square that, and I get 0.64. Now I got to do it for 5. So that's going to make, I'm going to take that original equation, 7.5 minus 0.9 times 5 times that x value. It gives me 3. So 2 minus 3 is negative 1. Negative 1 squared is 1. So that'll tell me the summation of my error squared for line A. I just need to add all this up. And it looks like I get 2.29. Now we can cheat and scroll down real quick and make sure I did the math right. Like, ding. Yeah, you see that? A was 2.29. So you would go through and you would repeat everything you did there with A for B. And if when you do B, so A was 2.29, and if you do B, you can see, I'll leave you to do B on your own, but you can see by the answer key you should get 2.64. And the only difference is when you do B, you're going to use the 8 minus 1.1 times all those x values. You still subtract from that y, you still square it, you still sum it, and you get 2.64. Your line of best fit, again, is the one with the smaller residuals, the smaller error, and our line of best fit comes out to be line A. So let me know if you had any questions on just determining a basic line of best fit.
I just wanted to clarify. So whichever has the overall smaller residuals would be the correct answer, the one that best fits. It's basically the smallest.
Yep, the smallest summation, because we're taking, so residual is just this part, right? So we're squaring the residuals because, and in statistics, we do this a lot. This way we don't care about direction. We don't care if it was less or greater. So we just square them. And we take the sum of those squares. So the one with, yep.
Oh. Thank you very much for that explanation.
Yeah, and you can go ahead then, on your own, you can try line B and make sure you do get the 2.64, but you will. So that is definitely going to be like a question on the test. I'm going to give you a small set of data. I'm going to give you 2 equations. You're going to show me the work, obviously, and you're going to tell me which of the 2 end up being. You're going to give me the sum E squared for each and tell me which of them end up being the line of best fit. Okay. Now, just because that is the line of best fit of 2 lines, it doesn't mean it is the best regression line for the equation. There's a whole process we have to go through to find a regression line. Okay. And that's what we're going to do in the second part. And it's a bit more complicated and a little more computations to go through and find that regression line. So what's going to happen on the test, just so you're aware, because finding the regression line, there's also multiple parts to that you can do after you find the regression line. I'm going to break this up. Like when you look at problem number 2, I'm going to give you a small set of data, okay? And then there's going to be a lot of A, B, C, D, E, F, G, H, a lot of parts to that one small set of data, because I don't want you to have to keep redoing these calculations again. So you're going to go through these calculations once, and then you're going to answer a bunch of questions that use those calculations. And the first question, is going to be about that line of best fit. What's going to happen on the test is I am going to give you these summations. These summations, we're going to take a look at the formula sheet in a second. You see what will help you immensely if you know these summations. So not only will I give you the data, I'll give you these summations. The first thing I'm going to ask you to find are these values. This S of XX, S of XY, S of YY. They don't have any, I'm trying to figure out the best way to say they don't have any meaning, but they really don't have any meaning. They're called like intermediate computations. They're really good. Once you compute them, you can use them for a lot of different things. And they're basically, you'll see by the formulas in a second, they're kind of like, I'll show you the formula and we can go over what they mean. But calculating those values allow you to do a lot of different other things in a regression equation. So I don't have a lot of space on here. I wish I did. So we're going to have to kind of do this, and I'll have to erase and so let's start with the first one. Because once we get all these values, which I don't have them pre-calculated, unfortunately, but there's something you're going to have to do on the test. So you got to know how to calculate them anyway. Let's go to the formula sheet, which I have here. Okay, so look up here on your formula sheet where you have the formulas for these values. They're really just kind of like the one we just calculated with the residuals. They're the difference between each X value and its average squared. The Y values are the difference between each Y value and the Y average squared. And XY is just the difference between each X and its average, each Y and its average multiplied together, okay? Now, that would take a really long time to go through that. So we're going to use the second set of formulas, which is much, much easier because of the numbers I already gave you. We're just going to use those formulas. So we're going to start with S of XX. And one of the things I want you to notice on the formula first before we go over to the other sheet is the difference between the summation of xi squared without a parenthesis and the summation of xi parentheses squared. And you'll notice that difference when I plug the numbers into the equation. So let's go back to our sheet. Okay, so the first one I need the summation of each xi squared minus, oh, sorry, an email came in and it screwed me up because, one second. There, I turned my email off. Hopefully that'll help. There you go. I think we're back. Minus okay, so let's plug everything in. The summation of xi squared, that's given to you. It's right here. I thought I turned the emails off. That's all right. That's 7,703.62. Now, the summation of xi is this number, the 188.2. You're going to square that and divide by n, and n is 1, 2, 3, 4, 5. So let's go ahead and plug that into the calculator and get that value. And you want to make sure you put it in. I'm going to jot them down here as I do them. And I just want to check to see if, I'm not sure if I have them all listed on the answer key or not. No, I didn't think I did. I thought that was a problem I added later, so. So I'm going to move forward and do the same thing for the Y value. I'm just going to double check that I put all that in correctly. Yeah, and if it's off a little bit, that's fine. I think that was a 2 and I put a 7, but it's so far off, it doesn't matter. And then for the Y, you do the exact same thing. You can take a look at the formula on your formula sheet, but it's the same idea. William Austin. It's going to be the summation. Sorry. This is why I hesitate doing office hours at night, because I get so many interruptions. I do apologize. Okay, so the Y squared is 242 minus summation of Y, 32 squared over 5. So that's going to be SYY. It looks like I get 37.2. And the SXY is a little bit different. You can just glance at the formula. That one's going to be summation XY and then each of them separate. So that's going to be summation of XY is 1136.4 minus. Then you take each of the summations. The 188.2 times the 32 over the 5. And we get negative 67.88. And by the way, the summation of XY value is the only one that will ever possibly be negative, because it's the only time you're not squaring something. So sometimes that one's negative. Questions on just doing those calculations?
So just to make sure, the equation for the SXX and the SXY are the same, but the only one that's different is the SYY, right?
Yeah, they're the same, except, you know, one uses the X's, one uses the Y's. The XY one, so if you take a look at the 3 equations, it's the 3 on the end. You can see the X, they're kind of the same, but this one uses the summation of XY together, and then they're 2 summations separate.
Oh, okay.
So that's why in here I did their summation together, which again, these are values I'm just going to go ahead and calculate ahead of time for you, so you don't have to spend so much time calculating stuff. So that their summation of X times Y, that's if I multiplied them all together and added them up, I get 1,136.4 minus here's your summation of just X, times here's your summation of just y divided by n. So you're going to see in a minute, getting these three calculations and having these numbers will just help us get that regression line. Because that's our first goal, is to come up with the regression line that fits this data. You know, because this is like a set of data that is slightly going down, I would believe. So somewhere there's the best line that is, you know, closest to all the data values. That's our goal here. And once we do all this work, we have a formula for that. So again, we go back to our formula sheet, and you can see here, here's the regression equation. And like any regression equation is just a linear equation. If you looked at any of the videos, I kind of went through how the very first video, how it's a little bit different. BO now is B sub O is our Y-intercept, and B sub 1 is our slope. So we just kind of changed notation a bit. But just like any linear equation, we need to find the slope. And here's our slope. It's S of xy divided by S of xx. So that's the first thing we're going to do, is we're going to get the slope. So the slope, B1, is S of xy, which is that negative 67.88, divided by S of xx, which is the 619.822. So we can go ahead and divide those. And I'm just going to round it 2 decimal places to 0.11. So that's what I got for my slope. Well, it's negative. Forgot the negative sign. Negative 0.11. And then once you have slope, there's a couple equations for the B sub O, which is the Y-intercept of the equation of the formula. The first one we're just going to use only because we don't have Y bar. I mean, you can go ahead and find Y bar and X bar, the mean of the Y and the mean of the X, or we can just use this first formula because it gives us everything we need, which is 1 over n, summation of Y sub I, minus that slope times summation of the xi's. So it's 1 over 5 summation of the y's, the slope times summation of the x's. So we can go ahead and calculate that. It looks like I get 10.554. So if those numbers are correct, and I did all my math right, my regression line is 10.54 minus 0.11x. There it is, done. So I'll stop there for a second and see if anybody has any questions. Okay, good. We're in good shape then. So that's the first part. So again, this is going to be like multiple steps. The first step, finding all those calculations. The second step, you're going to have to find the B sub 1, B sub O, get that regression equation. And then there's going to be more kind of follow-up questions. And this came from chapter 14. And the next thing it says, determine the percentage of the variation in the observed values of the response variable that is explained by the regression. That's called your coefficient of determination. A coefficient of determination, if you're not sure, go back and watch that video. It's a percent. And it's the percent of the Y values that can be explained by the X. So in some of the videos I talked about, number of hours you study in your test grade. So how it kind of tells you how effective the number of hours you study or how much it can really predict what your test grade is. It puts a percent on that. Obviously, the closer to 100, the better a predictor it is. So that's what we're looking at right now with our coefficient of determination. And that is also called our R squared. So let me get rid of this for a second. We have them. I'm going to write it down here so we don't lose it. It was 10.54 minus 0.11x. So the coefficient of determination is R squared. Go to your formula sheet. R squared is SSR divided by SST. So what happens is, and again, this is explained in one of the videos, there's regression sum of squares, which is the difference between the raw data and the actual regression line. And then there's total sum of squares. So the higher the 100%, your regression sum of squares is almost the same as the total. You're going to be very close to 100%. But if your regression sum of squares is much lower, you're not. Your total is made up of the regression sum of squares, which is from the regression equation, and then just error, the error sum of squares. If there's more error than there is with the regression line, you're going to get a very low percent. So here's the good news, though. SST itself, if you this is why it's really important to know your formula sheet really well. SST, you already have calculated because it is exactly equal to SYY. So that part's done. We can plug that part in. SYY we found to be 37.2. So what we need to find is this thing called SSR. Go to your formula sheet. Don't use the first formula because that would take you forever, but you can use this one because you've got those values. So it's the XY squared over XX. So it's XY squared. So it's that negative 67.88 divided by 619.822. Let me just make sure I wrote that down correctly. Yep, we got it. So let's go ahead and calculate that. Is when it can only has to come out. So we got 7.4. And when I divide those, I get really close to 0.20. I get 0.199836. Which I think we did everything correct because I believe that answer is given. I'm just going to double check to make sure. Yep, 20%. Perfect. If I wasn't dealing with a hot water heater all day, I definitely would have calculated these out ahead of time. And what's nice about this R squared, you'll know you did it wrong if it's not between 0 and 1. Because now we're going to convert it to a percent. And that just says 20%. Only 20% in the variation from the regression can be explained by the regression line. That's not very strong. So that what that tells us actually about our regression equation, if we were to graph it, the point it says it's restored. Okay, we're just going to keep going then. So if you have a regression line and those points are really close to it, you're going to get a really high percent here, like 90%. But if we were to graph this and the points are really spread apart, you're going to get a low percent. So that's kind of what that percent tells you. And again, that's called the coefficient of determination. And it's always represented as a percent. And it's always R squared. The next thing you would look for is a correlation coefficient. I'm sure you've heard about correlation before. How much is X correlated to Y? What you need to remember about correlation coefficients is they can be negative, where the percent for the coefficient of determination can only be between 0 and 1, a positive percent when you convert it to a percent between 0 and 100. The correlation coefficient itself goes from -1 to 1. And that is represented by just an R. So you can see it here. The linear correlation coefficient is R. We do not need to use that crazy formula. There's a couple things we can do here. We can use this formula. Okay. The S of XY divided by the square root of S of XX and SYY. So let's go ahead and do that because we already have all those numbers. So R equals the -67.88 divided by the square root of 619.82 times 37.2. And you should get -0.45. Now, it is not a coincidence that one is R squared and one is R. You can also take the square root of your R squared value and you will get the same thing. The problem is you lose whether it's negative or positive. You're always going to get a positive if you do that. So you have to think about whether or not the correlation truly is positive or negative if you choose to kind of go like the shortcut route, I call that, by just taking the square root of R squared. And here's the really easy way to determine whether it's negative or positive, if you have a negative slope, you're going to have a negative correlation. If you have a positive slope, you're going to have a positive correlation. So you can calculate that R value either way. This is going to be a negative correlation. So that means as our X value increases, your Y value decreases. Okay? We would call this a moderate negative. Sorry, why did I say positive? A moderate negative correlation. Strong correlations occur near -1 or +1. No correlation occurs right at 0. So clearly, if you're anywhere near -0.5 or +0.5, that would be considered moderate. If you're closer to the 1 and the -1, that would be strong. And if you're closer to 0, like 0.15 or 0.10, that would be a slight correlation. So this one's just moderate. We would not expect it to be very strong because our coefficient of determination was not very high. So it is a little less than moderate, but we can call it a moderate negative correlation. That kind of represents almost everything you're going to do with one particular problem from chapter 14. There is one other piece, and it's not on the review sheet, so maybe I'll add it real quick because we already have everything calculated. And that has to do with, from chapter 15, this idea of usefulness. Is this regression equation useful in predicting our Y values? Usefulness actually comes from the slope itself. And the idea with that is, so I would ask a question that would look something like, at the 5% significance level, do the data, I'm not going to write it all out right now, do the data provide sufficient evidence to conclude that, this is not in a context, so I don't know what the values are, to conclude that our X values are useful in predicting Y values. So I'm going to add this right now only because it's not on the sheet. So again, what you want to write down is, at the 5% significance level, do the data provide sufficient evidence to conclude, kind of like you see in every hypothesis test, that our X values are useful in predicting the Y values. Whenever you see this word usefulness, is something useful in predicting something else, we are going to run a hypothesis test for slope. This is our hypothesis test for slope. Because when you run a hypothesis test, you're doing predictions on the actual population data. That small b sub 1 becomes a capital B sub 1. So the way we would do this is to say, that your null hypothesis is your slope equals 0. 0 means not useful. Because think about it. If you have a perfectly, a 0 slope means you have a perfectly horizontal line, there's really no regression going on. There's no correlation between those two values. It's not useful. 1 is not useful. X is not useful in predicting Y. So our null is automatically, it's not equal to 0. And that means it is useful. we have a test statistic formula for that. It's right here on your formula sheet. And it starts, of course, so anytime we run a hypothesis test, we go back to the sample data. So it starts with our lowercase b sub 1, which is our sample slope. And then it's usually divided by some sort of standard error or standard deviation, and that's what SE is. SE is the standard deviation of all those residual values. So we're going to use SE divided by S over the square root of SXX. So we know B sub 1. We did that. B sub 1 was negative 0.11. We know S of XX, the 619, I'm just going to use 0.8. The only thing you don't have is SE, because we haven't calculated that yet. But the good news is we've got a formula for that too. It's right there. SEE over n minus 2. So you're going to find that when you try to do one thing, you have a new term. So you go up. There's the formula for that. If you don't know what SEE is, you come up here and you can calculate SEE. Okay? So one of the things, obviously it's a little different because you're not taking the test in class. You can relax a little more, but you really do need to know how to use this formula sheet where everything is on the formula sheet. So let's go back to the problem. So SEE is, SEE divided by n minus 2. SSE, not SEE, sorry. The only thing I have is I erased the other value I needed, which was SSR. Do either of you have the value? Sorry. So we can get SSE from what we call our identity, our regression identity. We calculated SSR a little while ago, but I erased it from my screen. So I don't know if either one of you have that by any chance.
I've just been writing down the steps for completion. I don't have the actual value.
No, that's okay, because we can use another formula to do that. We'll just use the formula. It's fine. It's shorter if you had that, but we can do it this way. There's a formula for SSE we can get.
The person in the chat says it might be negative 7.4. He's unsure.
That might have been it. Let me see. Oh, there it is, the chat. Negative 7.4. I do recall that. I completely, because I needed this space. SYY we know. I mean, SST we know because it's the same as SYY. So let's try the negative 7.4. I think that was it. So we have this thing called a regression identity. Okay. And SST itself is the same as SSY, so we have that. I mean SYY. Sorry, I keep flipping back and forth. My dog's barking like crazy. Yeah, that does make sense because it would be a small number. So 7.4. So all you got to do is subtract those two. So yeah, we had found the other two in this previous step, so you just have to subtract them. And it's 29.8. So SE itself is that 29.8 divided by, you can see it here, n minus 2. And take the square root of that. I gotta let my dog inside because she's going to keep barking. All right, let's get this number real quick. Divided by 3, second square root. It looks like I get 3.15. So I'm getting a really small number, like 0.004. I don't know if that's correct because I've got just craziness going on right now with everybody. Hold on. Oh, I see. This is it. All right. Negative 0.423. Looks like I got about this, somewhere around there. From that point, you can run a critical value. We're not going to go into that right now, or a p-value approach to finish a hypothesis test. My guess is that is going to come out of reject. It's a pretty high test statistic, or far from zero test statistic. So my guess is it might come out reject. You'd have to look at a t-table to kind of take a look at that. I don't think I have a t-table on my sheet right here. But you would, again, complete that just like you would complete any regression equation. I wanted to just take a look at negative 4.23. It'll, if it's not rejected, it would be close to it, but I believe that's a rejection, in which case you would say you reject the null hypothesis. The X is useful in predicting our Y value in this particular problem. So that's like the biggest part of the test is going through a problem like that where you have one set of data. Keep, the idea when you're doing that is to keep all your value, your work neat. Unlike I did where I kept having to erase everything because I got a limited space here. Keep it neat on your notes so you can refer back and label everything carefully because you're going to use a lot of these same values over and over again. So you want to make sure you do that. And this is recorded, so you can go back and watch this at any time. What I want to do real quick, because I only have a couple minutes left tonight, is take a look at the residual plot, because that is something you are going to have to do on the graph. Let me just erase this. And let's take a look at this residual plot. And we'll just do a couple of the values just so you can kind of see it, because it's a little bit different. So the residuals, again, are those E values, which just represent the raw data that you get, the actual Y value, and then the Y value you would get if you use a regression equation. So in this particular one, we have applicants for a job, involves extensive travel in Spanish-speaking countries, must be proficient in Spanish test. Okay, the sample data were obtained in a study of relationships between the number of years applicants have studied Spanish and their score on the test. So years you study Spanish and how well you do on a Spanish test. So let's take the first one. The first one studied for 3 years and got a 57 on the test. When a regression equation was made, we plug in our 3 for X, and let's see what the predicted value of the test would be for someone who studied for 3 years. So we can do 31.55 plus 10.9 times 3. So the predicted value is 64.25. Well, this person didn't get a 64.25. They actually got a 57. So your E, your residual, is that 57 minus the 64.25. And that's a negative 7.25 is the residual. So you would do that for each set of data. So you would do that, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times. What a residual plot looks like, it's kind of this graph here, but what you want to do is zero out the middle of the x-axis. That's going to be your 0 value. And you say, okay, at 3, we're going to plug in a negative 7. Sorry, somebody's making me laugh. So at 3, if this is 0, you have to get all your residual values first so you know what the scale of your graph is. But if this is 0, negative 7 is going to be, somewhere down here. So that would be our first plot. Now to plot the next number, you have to plug in a 4 to your regression equation and then find the residual at 4. What's going to happen at 4 is because we have 1, 2, 3 different test scores for people who studied Spanish for 4 years, you're going to have 3 different points at the 4. Okay, whatever those residual values end up being. At 2, you're going to have 2 because there's 2 at 2, so you put those in. I don't know what the graph is down here. You can kind of see it, what it looks like when it's done. You see that? So at 4, there's your 3 values at 4. That was our negative 7 that we found. So I just kind of wanted to set you up. But I am running out of time now, so I'm going to turn the recording off and just see if you had any other last minute questions or anything.